guys, welcome to our first video for Chapter 6. In Chapter 6, we're going to be using some radical expressions. We've done quite a little bit with radical expressions in Chapter 4. We talked about simplifying things that were in the form of square roots. In Chapter 6, we start looking at things that might not necessarily just be the square roots, but now we're going to look at things like third root and fourth root and fifth root, etc. So a couple of terms and terminology that we have to kind of talk about a little bit first. It says the nth root of a for an integer n greater than 1. If b to the n is equal to a, then b is the nth root of a. And so what we're really saying here is we're saying that the nth root of a is equal to some number b because b to the n power is equal to a. Now we're familiar with that idea. We've been talking about the square root of, say, 25, and the square root of 25 is 5 because 5 to the second power is 25. Now we can talk about things like the third root of 8 is equal to 2 because 2 to the third power is equal to 8. So this idea of taking other roots besides just the square root is going to be kind of permeating as we go through Chapter 6. The index on the radical, basically it's that number right there. We've so far only talked about the square root, and so there's kind of like an understood 2 here, sort of like when we have like 5x squared minus 2x. Sorry, that doesn't really work. Let's go with x squared plus 5x. We understand there's a 1 there. There's certain conventions that we just understand mathematically. If we don't write a 1 there, we assume there's a 1 there. If we don't write an operation between 5 and x, we assume it's multiplication. So if we don't write an index here, we assume that it's square root. But realistically, I suppose you could put a 2 there because we're saying we're taking the second root of a number. But again, we conventionally don't do that. All right. So again, the index of the radical is that number here on the radical sign. All right. Okay, so getting into then some actual work down here below, let's take a look at the next little box of information down here. It talks about the real roots of, the real nth roots of a number a. And so we kind of have to divide this chart into 2 here. Kind of looking at 2 scenarios. First of all, if n is an even integer. So what we're saying is if the integer out here on the root is an even number. So for example, square root, fourth root, sixth root, eighth root, etc. All right. So if n is an even integer, we're saying that this number under here that we're taking the nth root of, we had to have raised some number, b, we'll say, to an even power and gotten a. So let's think about this number b. Whether it's positive or negative, if I raise it to an even power, this is always going to be positive. So sort of like when we talked about the square root of 25, well, the square root of 25 is 5 because we know that there is a number that I can square and get positive 25. Now, if I asked you to take the square root of negative 25, well, that would be the same thing as 5i, but it's not real. It's an imaginary number because, again, the only way to get negative 25 is if we square 5i, which effectively would be 5i squared, which is 25 times negative 1, or negative 25. All right, so we can't take the even root, these are even numbers, we cannot take the even root of a negative number, otherwise we get things that are imaginary. Now, just remember that the square root of negative 1 is I. We don't have anything special for the fourth root or the sixth root of negative 1. So we're not worried about that right now, but basically we're saying this. If the number under the radical is negative, if it's less than 0, then there are no real nth roots because you can't take the even root of a negative number. All right. Again, if this number is even and this is negative, you can't do that because we can't raise some number b to an even power and get something that's negative. It's always going to be positive, at least in the real numbers. Right? We define that I for Chapter 4. How about if a is equal to 0? Well, it has one real root. It's 0. All right. And if a is greater than 0, now we can think of 2 numbers that we can raise to that even power. All right. And so it would be plus or minus a to the 1 over n power, and we'll kind of explain a little bit more about what that 1 over n means. But basically, you get 2 real roots, 2 real nth roots. So it has 2 solutions. All right, going to the other side. What if n is odd? What if the index is, say, the cube root, all right, or the fifth root, or the seventh root, right? Those would be odd roots. And so if we're taking an odd root, the odd root of a negative number is going to be negative, and so this is going to be a to the n power, or 1 over n power. And again, we'll get more into that rational exponent in just a little bit here as we get into the next page. But basically, the key is that it's going to have one solution. If it's a equals 0, well, the nth root, odd or even, okay? Basically, what number do you multiply by itself a whole bunch of times, whether it's even or it's odd, and get 0, and it has to be 0. And then finally, if it's positive, we also get one real root. It's a or 1 to the n. So let's try an example. Let's do, for example, the third root of positive 8. Well, we're asking then, what number can I multiply by itself 3 times and get 8? Well, obviously that number is 2, because 2 cubed is 8. So the third root of 8 is 2. Now let's change that up a little bit. Let's go the third root of negative 125. Okay, now we're going to say, what number did I cube and get negative 125? Well, that number then has to be negative, because we're going to multiply a negative number by itself 3 times, and the product of 3 negatives is negative, so this number is negative. And then the cube root of 125 is 5. And so if I cube negative 5, I will get negative 125. So basically, if the number is negative, we get a negative root. If the number is positive, we get a positive root. All right? So let's try some examples here. So we'll talk a little bit about finding some roots here. All right. In the first example, it says we want to find n equal 3 and a equals negative 64. So basically what they're saying is, we're saying, what is the third root of negative 64? All right. It says because n is equal to 3 and it is odd, and because a is negative 64, which is smaller than 0, negative 64 has one real cube root. By the way, if this is third power, we call it third, or if it's third index, we call it third root. If it's second power, we call it square root. If it's fourth root, we don't really have anything special for that. We wouldn't call that a quartic root. It would just be the fourth root of, okay? In any case, because it's odd and because it's negative, we know we're going to get one real cube root. And because negative 4 to the third power is negative 64, we can write the third root of negative 64 equals negative 4. And again, we'll talk more about this rational exponent in just a few minutes, but that's also negative 4. So again, don't worry about that right now. That's coming on the next page. Because in the next one, now we want the sixth root of 729. So we're asking ourselves then, what number did I raise to the sixth power and get 729? Well, obviously the sixth power is a pretty large number, but because this is, first of all, because this is an even root, the only way we can take the even root of a number is if it's positive. In this case it is, since it's greater than 0. We know that we're going to get two real solutions, or 2 real sixth roots. Okay, because again, there are 2 numbers that I can raise to the sixth power and get positive 729. What are those numbers? Well, because 3 to the sixth power is 729, and negative 3 to the sixth power is also 729, we can write plus or minus the sixth root of 729, which is plus or minus 3. And again, this rational exponent, don't worry about this. This is also plus or minus 3. All right, so let's try a couple of checkpoints down on the next page. Pause your video. Please try them. We'll be right back with solutions. All right, so our solutions for number 1, again, we want the fourth root of 256. So what we're saying is, what did I raise to the fourth power to get 256? And so as we know that that's the same thing as 4, because 4 to the fourth power is 256. Since we're taking the even root of a positive number, we know we're going to get 2 solutions, plus and minus 4. No different than when we took the square root of, say, 25. Square root of 25 is plus or minus 5, because there are 2 numbers I can square and get 25, both positive and negative 5. All right, what about the third root of 512? Well, the third root of 512, again, this is odd, so it doesn't matter if this is positive or negative. In this case, because it's positive, I know my answer is going to be positive, because the only thing I can cube and get positive 512 is a positive number. And the number 8, if I do 8 to the third power, I get 512. All right. Now, tomorrow or the following day when I see you in class, I will show you how to do some of these roots in your calculator. There is an option to do that on your calculator, but you kind of have to understand what this kind of means and what does it mean to take the third root of 512. It means what number did I cube to get 512, and that happens to be 8. All right? All right, so new definition, rational exponents. First of all, rational numbers, anything that's rational is a fraction, right? So when we start talking about rational exponents, basically we're talking about exponents that are in the form of a fraction. All right, now some of you guys that don't care for fraction much, you know, this is going to be a little bit challenging for you, but it's just a different way to think of a radical. All right, so it says let a be a real number and m and n be positive integers where n is greater than 1. And again, if n was equal to 1, then we'd just get m over 1, which really wouldn't be much of a fraction. And so it has to be like the second or the third or the fourth, whatever. Okay? All right, we can split this up into a to the 1 over n, then raised to the m, or we can also say that this is the nth root of a to the m power. So effectively what we're saying is the denominator of that fraction is the index on your radical, and the numerator is effectively just a power. All right, we can pull that m power out here and do this as a to the 1 over n, or as we said, this n becomes the index on the radical. So this says take the nth root of a, the base, and then we can pull the m out outside. Again, same thing before, negative exponents immediately go to the bottom, and so this becomes 1 over a to the positive m over n. Once again, a to the 1 over n tells me it's the nth root of a, all raised to the m power, provided that a is not equal to 0, because if a is equal to 0, the whole bottom is 0, and we would get no solutions. Okay? So let's take a look at a couple of examples here. We're going to do this exact same problem using rational exponent form and radical form. So we can do this both directions. And you have to be comfortable with both. First of all, anything with a negative power immediately gets put downstairs. This is 1 over 8 to the 4/3 power. Now, in using rational notation, this becomes 1 over 8 to the 1/3 power, then raised to the 4th power. So this is a 3 in here. I know it's kind of hard to read. So now what we have is we have 8 to the 1/3 power, which effectively says what's the third root of 8, and that happens to be 2. So this is 1 over 2 to the 4th, which is 1 over 16. Now, for me, this is harder to recognize, so I'm going to do it with radical form. Again, the same thing goes. This is 1 over 8 to the 4/3 power. And then I'm going to write this 1 over, and I kind of have to put my fraction bar sideways a little bit, sorry. This becomes the third root of 8 to the 4th power. So because this number right here is my index, all right, that's my index on my radical sign, so it becomes the third root of 8, and then the third root of 8 is 2. So this becomes, sorry, it's going to squeeze over here, becomes 1 over 2, 1 over 2 to the 4th power, and then 2 to the 4th power is 16, and so I get 1/16 that way as well. All right, so whether you would like the rational exponent and knowing that 8 to the 1/3 power means the third root of 8, or if you want to write it this way, that's fine. Either way is just fine with me. All right, so let's solve a couple of equations that involve using nth roots. First of all, if we're trying to isolate the x to the 6th, if we were doing this back a couple chapters ago, we would divide by 2, whatever this comes out to be, 128, and then I would take the square root of both sides if it was the 6th square root, or the second power. Now we're dealing with the 6th power, so big deal, right? Let's divide by 2 and isolate the power, and 1458 divided by 2 is 729. Now, because I'm trying to get x alone, I have to take the 6th root of that, and the 6th root of x to the 6th becomes 6, or I'm sorry, just x. And now, remember, anytime we take the even root of a positive number, we have two solutions, plus or minus. All right, and this becomes plus or minus the 6th root of 729, and the 6th root of 729 is 3, so my two answers are plus or minus 3. So what we're saying is if I take positive 3 to the 6th power and multiply it by 2, I'm going to get 1458. If I take negative 3 to the 6th power, that's also going to be positive 729, and I multiply that by 2 and I get my 1458. Okay? All right, we don't have to consider two possibilities here. Okay, first of all, the third power is isolated on the left, so we don't have to do anything like get rid of the 2 like we did here. We do not want to expand this product. Okay, that's not going to be our best option for a solution here. All right, instead what we want to do is we want to take the cube root of both sides, and the cube root of 12, we're just going to write that right now as the cube root of 12, because if I take the cube root of both sides, that eliminates the third power. And so now I have x plus 4 is equal to the cube root of 12, take away 4 from both sides, And so it becomes the cube root of 12 minus 4. Well, the cube root of 12 is approximately 2.29. And then if I subtract 4 from that, I get approximately negative 1.71. Now notice here we didn't have to consider plus or minus here, all right, because we're taking the odd root. So we don't have to consider plus or minus. All right, next page, we're going to take a look at a practical example of this. The animal population of a certain animal species over t months can be modeled by the equation P equals C times 1.21 raised to the t over 3 power, where C is the initial population and the population after 19 months. Find the population after 19 months if the initial population was 75. So again, C is my initial population, so essentially I'm going to put my 75 here. So this becomes 75 times 1.21 t to the 3rd power. And we want to know after 19 months, right? 19 months, so this becomes a 19. All right, and so I'm going to clean this up a little bit. Let's get rid of that. And let's change that to a 19. And so this becomes 75 times 1.21 to the 19/3 power. Now, there's really no way to do this without using a calculator. We have to raise 1.21 to the 19/3 power and then multiply by 75. And so we're going to run over to our graphing calculator and pull this up. And we're going to go ahead and we're going to type that information in. And so our number was 75 times 1.21. And I want to raise that to the, now to get that rational exponent, I want to use a parenthesis to say that I'm going to raise this to the 19 over 3 power. And so we go ahead and press enter, and it's approximately 250. And again, this is going to be 251, approximately 250.8, so we're going to go about 251. And so let's go back to our pen here. And this is about 250.8, so roughly 251. So we have a population of approximately 251 animals after 19 months. All right, so let's run through a couple of checkpoint problems. You guys try these, and we'll be right back with solutions. I do much better with with radical notation. I don't know if you will or not, but I'm going to probably do a little bit more with the radical notation. Since this, not because this is negative, but because this is negative. The exponent's negative, so I'm going to make this negative 125 being raised to the positive 2/3 power, because again, if it was negative exponent on top, we move it to the bottom and it becomes a positive. All right. Now, once again, I like radical notation better, so I'm going to use the radical of 3rd root of 125, all raised to the 2nd power, and don't forget there's a 1 on top of here, right? And so the 3rd root of negative 125 is simply negative 5. So this becomes, right here, becomes negative 5, and I'm still squaring that. So this becomes 1 over 25. All right? We don't have to consider plus or minus because we took the 3rd root, so we do have to keep the negative here. But when I square it, it becomes positive anyway. All right? So let's take the 4th root of both sides of this because I want to isolate this y minus 3. And so to get rid of 4th power, we take the 4th root. Y minus 3 equals the 4th root of 200. Now, the 4th root of 200 does not come out to a nice number. In fact, the 4th root of 200 comes out to approximately 3.76 according to what I have here. And so remember though, when we take the even root of a number, we always have to consider plus or minus. And so we're going to add 3 to both sides of this thing. All right, and so y is equal to 3 plus or minus the 4th root of 200. Now, as I told you, the 4th root of 200 is 3.76 or something like that. So if I do 3 plus 3.76, I get roughly 6.76. And if I do the 3 minus 3.76, I get roughly negative 0.76. And so since those numbers don't come out very pretty, we're going to go ahead and leave them as decimals. But I guess the 3 plus or minus the 4th root of 200 would have been a perfectly acceptable answer as well. All right. The volume of a cone is given by the equation V equals pi r squared times h, all divided by 3, where h is the height of the cone, r is radius. Find the radius of a cone whose volume is 25, so we're going to put the 25 in for volume, equals pi, and we're looking for, it says find the radius, so that's what we're looking for. Multiply that by the height, and it tells us the height, which is 6, and the whole thing is over 3. All right, let's simplify first. 3 goes into 6 twice, and so we can make this a little bit easier on ourselves. So I have pi times r squared times 2, and so now this becomes 25 equals 2 pi r squared. I'd like to put the 2 in the front if I could. I'm going to divide both sides by 2 pi, and I get r squared is equal to whatever 25 divided by 2 pi is. And now to isolate the r squared, I have to take the r rather, I'm going to take the square root of both sides. Now when we were solving in the previous example, we had to do plus or minus. In this example, since I'm talking about a radius, I don't need to have plus or minus, because the radius has to be positive, right? So r is going to be whatever the square root of 25 over 2 pi is. All right? So we'll fire over to our calculator, which is right... Sorry. We fire over to our calculator, which is right here. And we are then going to do... Now listen, if you do 2 pi... I'm sorry, we want 25 divided by 2 pi, right? If we do 25 divided by 2 pi, like that, you're going to get 25 divided by 2, and then it's going to multiply the result by pi. We want 2 and pi in the denominator, so make sure you put parentheses around that. So 25 over 2 pi is going to be what r squared is, and then remember we want the square root of that, so we're going to take the square root of that answer, and I get approximately 1.99. So that tells me that the radius of this is roughly 1.99. And all of these units were in, let's see, cubic inches and inches, so that must mean that this is in inches. All right, and so that concludes our first lesson on Chapter 6.